Hi, my name is Chima Kunzung. I'm a software engineer at Protocol Labs, and today I will be giving a brief survey of some projects spanning diverse domains linked by common threads of research and development. This is really at least two talks squished into one, so I decided to try to highlight the themes which connect all of this work. I'm going to have to move fast to get through it all, so I apologize for what will necessarily be a superficial treatment. I work in a team called CryptoComputeLab. We implemented the Filecoin proofs and have continued to maintain and improve them. However, in the years since Filecoin mainnet launched, we've also turned our gaze to the horizon. Today, I will present a few of our longer-term projects which span low-level optimizations, high-level abstractions, hardware manufacturing, and prospective cryptographic systems that are literally out of this world. Okay, so the first topic is VDFs. VDF stands for Verifiable Delay Function, and some of you might know this. This might be new to others, but a VDF is a function that is slow to compute and fast to verify, and we can use it to ensure that a minimum time has passed. So, for example, if we have function f of an input x with a time parameter t, then y is going to depend on x and take at least time t to compute. And to get an intuition for fast verification, we mean even if t is high, like 100 years, verification time should remain low, like milliseconds. Okay, so what's an example of a usage of a VDF? On a blockchain, you might want to prevent grinding on deterministic pseudo-randomness. So if the chain is going to compute a random number based on a public value that the user can influence, the user might try to brute force that and get a good random number, whatever that means. So we can stop that by making it take some time for the randomness to be computed so that the user isn't going to know whether their number is good or not until it's too late to try to change it. Another example comes from the Filecoin domain. If you're familiar with the proof of space-time, one thing we could potentially do is let storage providers perform their post on regular intervals, but only submit those proofs less often in order to minimize the chain bandwidth. But the problem is we need to be able to prove that the post happened at the right time. The attack is that the provider actually throws away their data and regenerates it, and they do all their posts all at the same time right before submission. So if we have a VDF, we can separate those posts and make sure that a fixed time passes between each one. But this actually requires a very good VDF, whatever that means, which we'll talk about a little more later. Okay, so this is the slide with a lot of information about a computational VDF. You might have to just look at it and see what you can make of it. The main point is that a forward direction evaluation, which you can see in my diagram here, is slow because exponentiation to a large power requires many multiplication operations, which your computer has to do. But the inverse direction is fast because the return trip is shorter in a finite field where we have modular arithmetic. This is an oversimplification of the min-root algorithm, but it's generally what we use. There's something called the AMAX, which stands for Attacker's Maximum Advantage, which is an important concept with VDF. Important general concept with VDFs, which is basically how much faster can an attacker compute this function than an honest party who's using the regular function that everyone's supposed to use. And the lower we can make that, the better. So we're working with a company called Supranational, and they have made an optimized CPU evaluator already, but we need to go even faster to bring that AMAX down more. So part of this work is to design and build an ASIC. The better our ASIC can be, the more an attacker is going to have to spend to try to get an even better ASIC. So this is the hardware computation-based approach. The limitation of this is that even the best hardware VDF we could possibly build is not going to be actually optimal. Hardware is always getting faster. So we're not going to get an AMAX that is practically 1. And unfortunately, that's what we would need for this Filecoin example that I gave this periodic post. This is where the idea of a latency-based VDF comes in. If we want to get an AMAX that's practically 1, we need some kind of a hard speed limit we can actually reach. So how about the speed of light? So we're working with a company called CryptoSat, and we're investigating the idea of a space VDF, where we would have secure satellites placed in publicly known positions. NORAD tracks this, so it's fairly discoverable whether they really are where they're supposed to be. They'll generate private keys in space, and as long as those aren't leaked, then the physical locations of the signatures that they make will be known, so we can establish a minimum time between sequential signatures. So we're in the early stages of this, but CryptoSat is conducting a system-level trade study to figure out which parts of this are actually viable and how it would work, so we can actually do some Filecoin orbit stuff. We talk a lot about the space metaphor, but here's an actual space project, which is fun. So how do we do these proofs? Verifying one step is always fast, like I showed you before, whether it's a small exponentiation or verifying a message signature. But when we want to make many steps, we need to for a long delay, these things are still stacking up. So we can use a snark and prove many steps at the same time. But it still doesn't solve the general problem. And the general problem is that whatever the actual rate, the proof size and verification time are still going to scale linearly with the delay time. So can we snark the snark? The historical answer to that is, well, it's not quite so simple. That is a complicated thing to do. But nowadays, it turns out, yes, we can use recursive snarks. I drew a picture here that gives you some kind of an idea of what that might mean, but we don't have time to talk about it in detail. So we'll just move on. So this is it. We are building hardware and software optimizations for recursive proving systems. We're working with the Electric Coin Company, who you might know from Zcash. And we're also using Nova, which is a proving system coming out of Microsoft research. So Halo 2 and Nova are 2 candidate proving systems. They both use recursive snarks. They both work with the pasta curves, and they use different arithmetizations for the constraint systems. Either way, we're working on CPU optimizations for verification, GPU optimizations for off-the-shelf proving, and ASICs tuned for proving on these things. And the goal is to make creating recursive snarks 5 to 10 times cheaper. So this should be good for everybody. And that brings us to Metaproof. So Metaproof is a CryptoComputeLab project founded on our frustrations with the limitations of previous generation snark techniques that we had available to us when building Filecoin. With modern proving systems on the cusp of accessible recursion, we saw an opportunity to leap forward, and Metaproof is our vision for how to do that. So we want to decouple the proof specification from the underlying proving systems. Like, we don't write most of our software in assembly or logic gates, so why do we write our proofs that way? We want to write proofs that can be deployed to multiple proving systems like Nova and Halo 2. We want to have proofs that are about proofs. so that we can use the proving mechanism to help us know that our programs are correct. How do we know that our circuits are actually doing what we want them to do? This is hard to do. And we want to support general computation, especially in the domains of decentralized data. So writing proofs should feel like writing programs, and that's one of our goals. So recursion actually makes this possible. And we are going to build Turing complete snarks via recursion. What does that mean? So the traditional snarks like Filecoin has today are bounded. We have a circuit and we can only perform a certain number of calculations in each circuit. In Filecoin, we raised that limit to be very large, but at the end of the day, this influences the form of the computation we can actually perform. So we can't have unbounded loops, we can't have arbitrary control flow, we can't have unbounded recursion. And this makes it hard for us to write things that feel like normal computer programs and puts us in a box in terms of the kinds of proofs and protocols that we can design. So Turing complete snarks overcome these limitations, and everything that was, a no on the left side is a yes on the right side. So we'll have unbounded arbitrary control flow and unbounded recursion. Okay, so we have a Turing complete snark language in development. We call it Lurk, and there's a lot to say about it, but there's not really time here to do it justice. So we're going to open up this project hopefully by the end of the year, and at that point you'll be able to use this language to generate and verify proofs, and you'll see end-to-end examples with running code. Meanwhile, we can tell you that Lurk has a small core that implements a minimal Lisp. You can use that to evaluate arbitrary programs. Programs are data and vice versa, and the data is content addressable for compatibility with IPLD, IPFS. So there are a lot of approaches to Turing complete snarks. What we're doing is just one of many exciting things that a lot of groups are doing, but we're especially focused on the use cases that fit with Filecoin and CryptoComputeLab's is decentralized data centric applications. So hopefully we'll have that available by the end of the year. You can check out the repo and ask us questions there if you want to. And just to give you a sense of what this looks like and what's interesting about it, this is a slide that I took from a more detailed presentation, but I'm including it here because it shows a very small, self-contained and complete example. So this lets you see what the code looks like, and it also provides a minimal example of something that Turing complete snarks allow, but that is impossible with ordinary snarks. So specifically, this example allows me to prove both membership and non-membership of an element in a set of unbounded size. And the prover cost is linear in the actual size of the set. So there's a lot to unpack here, but if you can understand this example, you'll see many of Lurk's interesting characteristics. The main thing is if you're not used to thinking this way, and you happen to be able to read Lisp code, then this just looks like a short Lisp program that's inspecting some data. And in fact, that's what it is, and that's what's interesting. And so the Lisp data is the same form as Lisp code, which is this content addressable, snark-friendly IPLD. Like I said, a lot to unpack, but it's very exciting for us, me at least. So hopefully over time, we'll see the fruit of this. So Lurk is very expressive and legible, as you saw before. You might take issue with that if you don't like the way Lisp code looks, but it's also a natural target for other languages. So if you don't like that, build something else and compile down to it. We already have a number of projects that are either starting work on or planning to develop backends for Lurk. There's a lot of information here, so you might just want to read these slides. I'll talk over it a little bit, but we have Yatima, who's working on a Lean4 theorem prover kernel that integrates with IPFS and IPLD and will compile to Lurk. Nada Amin is a programming languages professor at Harvard, and she's working on relational programming languages on top of Lurk. And in fact, she's implemented already the core functional part of a language called microconren, and it only takes a little bit of code to do this in Lurk, which is neat. So she's looking to develop a relational layer on top of Lurk. There's an internal PL project called Verily, which is working on certifiable IPLD data and transformation for decentralized systems. And we're looking at targeting Lurk for that as well. And we're also working with a language called Glow for decentralized applications. That's a very close fit to have a zero knowledge proof backend for their programming model. And we have a first Filecoin specific application in mind for this. And this is verifiable computation over Filecoin sectors, which I think is super exciting. So Filecoin makes it cheap to store a lot of data, but what if you want to operate on that data without retrieving all of it? I don't want to have to transfer 32 gigabyte chunks of data every time I want to perform some kind of a query on my data. So let's say I have a database containing millions of weather records, and I want to know the average temperature in Lisbon on days in 2020 when it also rained. A storage provider could calculate this small result and return it along with a proof of correctness. And if that's verified on chain, this is going to allow smart contracts to interact with sector storage. So for decentralized computation to be efficient, it must be possible to eliminate redundant computation and co-locate the storage and computation. And this is going to let us do that. It's very early, but this is probably the most exciting application for me because it builds on Filecoin. So we're looking forward to working with the Filecoin virtual machine team, FVM team, to explore these possibilities and see what kind of interactions will be possible. So, in review, we're working on VDFs with optimized hardware and software, and we're putting satellites in space. And through that investigation of space and time, we were driven to investigate, support, and help develop recursive snarks. And this allows Turing completeness. So we developed a programming language that exploits that. And this lets us do many cool things, many of which we don't even know yet. But one of them is verifiable computation on decentralized data in Filecoin. So watch this space. The work is only beginning, but it's very exciting. Thanks for listening. These are all my closing parentheses. It's a Lisp joke. Thank you.